Imagine a universe where time does not flow in a straight line from past to future, where moments can ripple backward and causality becomes a tangled web of possibilities. For centuries, our understanding of time has been rooted in the idea of an unchangeable arrow, one direction, always onward. But recent breakthroughs in quantum physics challenge this deeply ingrained notion, suggesting that at the smallest scales, the fabric of reality may conceal phenomena that defy our most fundamental assumptions. Could it be that the universe harbors secrets of a reverse flow, where the future influences the past? As scientists edge closer to unraveling the mysteries of negative time, we are compelled to reconsider not just how we understand the universe, but what it truly means to perceive reality itself, a universe far stranger and more wondrous than we ever imagined.
In a groundbreaking development that stretches the boundaries of our understanding of reality, researchers at the University of Toronto have reported observing what they are calling negative time, a phenomenon that suggests the possibility of a flow of time moving backwards from the future toward the past. This discovery, rooted in the complex and often counterintuitive realm of quantum mechanics, challenges long-held assumptions about how the universe operates and raises provocative questions about the very fabric of reality.
Rethinking time from illusion to measurable reality. Historically, the concept of negative or backwards moving time was dismissed as an optical illusion or a mathematical artifact, an inconsequential curiosity in the vast landscape of physics. Conventional wisdom held that time was a one-way street, an unbreakable march forward governed by the second law of thermodynamics and classical causality. Yet, recent advances in quantum physics suggest that, at microscopic scales, time may not be as linear as it appears, and under certain circumstances, parts of its structure could momentarily bend or even move in reverse. This revelation gained credibility through experiments that employed the strange behavior of particles such as photons, particles of light that often defy classical logic. These particles, unlike everyday objects, can exist in multiple states at once, exemplifying the quantum principle of superposition.
Challenging the temporal barrier, a breakthrough in quantum experiments. Led by physicists Ephraim Steinberg and Daniela Angulo, the research team designed experiments to explore the interaction of photons with atoms. Their approach involved precisely measuring the time it takes for an atom to absorb a photon, and then re-emit it and process it in classical terms should occur within predictable timeframes. Using ultra-sensitive equipment, they tracked the duration of these interactions with extraordinary precision. What they found was startling. Some of the measured interaction times appeared to be shorter than zero, a result that on the surface suggests that photons somehow left the atom before they even arrived. While such findings seem to play with our notions of cause and effect, the scientists clarified that this does not imply actual backward travel in the classical sense. Instead, it signifies the quantum behavior where the notion of time becomes blurred, probabilistic, and sometimes seemingly paradoxical. Steinberg explained, "Our results don't mean you can flip a switch and travel back in time. Rather, they reveal how quantum mechanics sometimes produces outcomes that challenge our everyday intuition about causality and the flow of time."
The subtle artifacts of quantum mechanics, photons, and the fabric of reality. These experiments took place in a specialized basement laboratory filled with lasers, mirrors, and delicate sensors, reminiscent of the setups used in quantum optics pioneers' historical experiments. In such environments, scientists manipulate and measure photon behavior at the smallest scales possible, uncovering phenomena that seem to hint at the universe's hidden mechanisms. For example, when photons pass through certain materials, they are momentarily absorbed and re-emitted, changing their quantum states in the process. Traditional physics expects the timing of these events to be consistent, yet, in ALO's experiments, the interaction durations sometimes indicated that photons exited the material before they had fully entered. It's akin to witnessing a ball roll through a maze and suddenly appearing outside a wall before it even enters, a scenario that defies classical logic, but aligns with quantum probabilities. This paradoxical outcome underscores the inherently fuzzy and non-deterministic nature of quantum particles, which do not adhere strictly to linear timelines. Instead, they seem to accommodate multiple simultaneous states, creating complex superpositions that can produce outcomes challenging our conventional notions of time and space.
Skepticism in scientific debate, a contested frontier. Despite the compelling data, these findings have stirred debate within the broader scientific community. Some critics, like prominent theoretical physicist Sabine Hassenfelder, dismiss the terminology negative time as misleading or over-interpreted. She argues that what the experiments reveal are phase shifts, subtle quantum effects, rather than actual reversals of time. However, Steinberg and Angelo stand firm, emphasizing that the data, rigorously tested and replicated, open a window into previously hidden layers of quantum reality. They believe their work hints at a deeper understanding of how particles interact and how seemingly paradoxical effects are integral to the quantum world. This divergence in interpretation sparks broader questions about the language we use in science. Is it more productive to think of such phenomena as time manipulation, phase shifts, or quantum correlations? Regardless, these studies ignite curiosity, they challenge our assumptions, and invite us to reconsider the fundamental concepts underpinning our universe.
Broader implications from quantum computing to cosmology. While practical applications of negative time are still speculative, the implications are profound. Understanding how quantum particles can produce effects that appear to violate classical notions of causality could revolutionize fields like quantum computing, cryptography, and communications. For instance, if we can harness quantum effects that seem to involve backward influences, we might develop new methods of information transfer that surpass current limitations imposed by classical physics. Imagine quantum networks where data could be transmitted instantaneously or even in a way that sidesteps the usual flow of time, opening doors to technologies once thought impossible. Additionally, these findings could have ramifications for cosmology and the understanding of time itself. If, at the quantum level, time behaves in ways that defy classical understanding, it raises questions about the origins of the universe, the nature of black holes, and the possibility of parallel timelines or multiverses. Some theorists speculate that backward causality might be a key to resolving paradoxes related to information preservation in black holes or the nature of the Big Bang.
The nature of reality and the limits of human understanding. What's truly captivating about these experiments is how they challenge the very fabric of reality as we perceive it. They push us to rethink whether time is an absolute dimension or a flexible, emergent property that depends on the scale and context of observation. These results echo foundational debates in physics, Isaac Newton's certainty about absolute time versus the relativistic view introduced by Einstein, which regards time as intertwined with space and relative to the observer. The phenomenon of negative time exemplifies how quantum physics resides at the edge of human comprehension, often giving results that confound common sense. It's reminiscent of the early days of quantum mechanics, when phenomena like wave-particle duality and quantum entanglement initially baffled scientists. Now, with recent advancements, we're beginning to glimpse that the universe might operate with layers of complexity and subtlety that extend far beyond classical intuition.
A new paradigm on the horizon? While these findings may not instantly revolutionize our technology or daily experience, they mark a critical step toward a deeper, more nuanced understanding of the universe's fundamental rules. They invite scientists, philosophers, and thinkers alike to ponder profound questions. Is time an illusion, merely a convenient way for us to navigate our everyday world? Could there be modes of influence that ripple backwards from the future, or are we simply witnessing the quirks of quantum correlations masquerading as backward time travel? The controversy and curiosity generated by this research stimulate further experimentation, debate, and theoretical development. Future studies might explore how these effects manifest in larger systems, whether they can be controlled or utilized, and what they reveal about the true nature of reality.
Final reflection. In essence, the detection of negative time through quantum experiments exemplifies both the remarkable progress made in modern physics and the humility we must maintain in the face of nature's mysteries. It demonstrates how science continually evolves, peeling back layers of understanding to reveal astonishing truths that challenge our perceptions. As we venture further into the quantum realm, we may find that the universe's most profound secrets lie not in the definite, but in the indeterminate. The very realm where time itself can dance to its own enigmatic rhythm, sometimes forward, sometimes backward, and always beyond the reach of our preconceived notions. The discovery of phenomena hinting at negative or backward moving time pushes the boundaries of human knowledge into uncharted territory. It invites us to question whether our perception of time is an absolute truth or a convenient illusion shaped by our limited perspective. As science delves deeper into the quantum realm, we realize that the universe might operate on principles that challenge the very notions of causality, memory, and history, perhaps harboring a reality where the past and future are intertwined in ways we have yet to fully comprehend. In embracing these mysteries, we are not just expanding the frontiers of physics, we are broadening our understanding of existence itself. What truths lie ahead as we continue to probe the depths of time's enigmatic dance? Only time will tell. And perhaps, in the process, we will discover that the universe's greatest secrets are hidden in the moments we have yet to fathom.
If you enjoyed this video, give it a like, share it with your friends, and subscribe so you don't miss out on future ideas that challenge us to think outside the box. We'd love to hear your thoughts in the comments below. Until next time, and don't forget to always maintain that curiosity that drives progress. Also, explore even more fascinating content on our channel. From life-changing tips and cutting-edge technology, to the mysteries of spirituality, travel to various countries, delicious recipes, health hacks, and language learning, there's something here to spark your curiosity and elevate your life. Dive in and discover a world of knowledge awaits us.